Okay, so let's get started. Topic of today is to finish off actually the physical layer, hopefully. And what is remaining now is to try to assess the performance of the physical layer in terms of its data rate, probability of error, spectral efficiency, and so forth. So to do that, we need to model both the data that we transmit and the uncertainties of the channel in a stochastic framework. So that's the way to handle uncertainty, I would say, in general. So we will do a little bit of a review of the basic stuff of that and then continue to see how that could be applied in our setting. If we, a short review, what we have been talking about last time was the concept of a matched filter. So a filter which is matched to a pulse h has impulse response f, where f is a complex conjugated and time reversed version of the pulse itself. So very simple. If we have a pulse that looks something like this, h of t, then the impulse response f of t is a time reversed version of the pulse. So we just flip it, right? And then complex conjugate if needed. If it's real valued, of course it's not needed. So these matched filters are heavily used in receivers. And one particular property of this matched filter is that if we have a filter which is now matched to the pulse h and we feed it with some input signal r, we get an output y, and if we sample that at time 0, the sample we get, that is the value of y at time 0, is the inner product between r and h. And if you remember, the inner product is simply the integral of r with h conjugate t dt, like this. And that turns out to be a useful property in improving things for the receiver of pulse amplitude modulation. So in particular, if the input to the matched filter is some amplitude a times the basic pulse h, then the output, okay, so here's the input, then the output at time 0 is the inner product of the input with h, and then we can pull out 8 out of the inner product, and we simply get a times EH, where EH is the energy of the pulse. Energy of H of t. Okay, and this can then be generalized as follows. So if the received signal is a times h delayed by k times capital T seconds, then the output sampled at k times t, capital T, is again a, the amplitude which was carried by the pulse, times the energy of the pulse. Okay, so this property is then used in the receiver of pulse amplitude modulation. So a PAM block diagram looks something like this. We have some data, A, that needs to be transmitted. We use basic pulse h, and we transmit pulses every t seconds. And then we get a transmitted signal S, there's some noise, and then we get the received signal here. The first thing we do is to have a matched filter, and the filter is matched to the pulse that we use at the transmitter side. We get some output, and we sample that once every t seconds with the same rate as we're transmitting pulses at the transmitter side. And then we get some samples, y, and then we multiply them with 1 over EH, and then we get Z. And this is the input to the decision device to spit out our guess about what the transmitted data was. Okay. Okay, so this thing is called the slicer. And the output of the slicer is the amplitude in curly A that is closest to the input. Okay, so we take the input and we look in A, what is the curly A, what is the amplitude in curly A, which is closest to zk, and that is the output. Then one can show that this block diagram is a minimum distance receiver if there is no intersymbol interference. So with that statement, we mean that if h, t, convolved with the impulse response, which is h conjugate negative t, so time reversed version of h, if this is a scaled Nyquist pulse, then there is no intersymbol interference. So what does that really mean? Well, it means that if we take h, convolved with h conjugate negative t, we sample that every t seconds, then only one of those samples is non-zero. The one when k is equal to 0. Okay, so, and for all other values of k, it's 0. So we have one of these things that the sample at 0 is equal to EH. And then for each multiple of t, we get 0. Okay, so that is what this statement says, and what it is in between is inconsequential. It could be anything. So whatever signal I can draw between these circles is okay. So maybe, I don't know, this signal will do nicely, for instance. Okay, and what signal am I referring to? I'm referring to that signal. Okay, so under this condition then, that we have these zero crossings, so that h has this scaled Nyquist pulse, or actually h is, yeah. Then the input to the slicer, okay, so this z is this z. The input to the slicer is the data that we transmitted plus a noise component. Okay. The data that we transmitted we find here, and the noise component is whatever this noise, when it goes to this signaling chain, is what is the value of the noise contribution at this point. So we will talk much more about the noise component today, okay, to characterize that. Okay. So any questions on this before we continue? It's fairly important that this is pretty clear, right? Otherwise it can become a little bit confusing today, right? So if it becomes unclear, you know, just stop me and I'll try to explain. Okay, so the objective now is to look at this noise component, try to figure out what is it, how can we characterize that, and we will assume then that the noise is a random process, so it's a random signal, which means that we have some type of random characterization of this. So it's going to be random variables and random processes and so forth. So let's go through some basic review of this material that I hope you've seen before. If not, maybe you want to refresh it, and then there are some links at the homepage for good review material of this. If nothing else, we will talk a little bit about notational conventions here. So random variables, what are those? Well, these are things that model uncertainty. It's a quantity whose value we don't know before we observe it. So we are unsure about what the value of the quantity is. That's a random variable. So before I flip a coin, I'm not sure if it's going to be heads or tails. So then we can think of the outcome of the coin flip as a random variable, or rather the action of before I flip the coin, I'm unsure about what the outcome will be. Okay, so that's a random variable, for instance. Then there is this concept of a cumulative distribution function, or CDF, and a probability mass function for a discrete random variable. Okay, first of all, what is a discrete random variable? Well, it's a random variable that takes on a countable number of outputs, maybe all the integers, or in the case of a coin flip, 0, 1, or something like that, something which is discrete. Then one can define the CDF as the probability that the random variable has an outcome which is less than some number u. So u is a variable, and then this is a function. then there is this probability mass function, which is simply the probability that x takes on a certain value u. And when there are discrete random variables, okay, so for discrete, we will use brackets to indicate this. Okay, so to be really clear that what's inside the bracket is a discrete variable, so say an integer. Okay. For continuous random variables, which are variables which are not discrete, then one defines the CDF in a very similar way. So the CDF is the probability that the random variable is less than some number. When it comes to the probability mass function, there is no probability mass function for discrete random variables, but rather a probability density function. And the probability density function is defined as the derivative of the CDF. Okay. So one should not interpret the PDF, probability density function here, as a probability, because the PDF could be above 1. It could be more than 1, for instance. That's clear. And there is no probability higher than 1. It's always a positive number, by the way. Okay, and then we can compute probabilities using CDFs and PDFs or PMFs as follows. If I'm interested in the probability that the random variable is between A and B, I can use the CDF by just or splitting this probability into two probabilities. It's the probability that x is less than b minus the probability that x is less than a. Okay, and this can be written in terms of the CDFs. And if it's a continuous random variable, we can integrate the PDF to get that this number. Or if x is discrete, it's a sum instead over the PMF. So hopefully this is not too much news for you. Is it? No. Okay. So let's continue then. Expectations, or in Swedish väntevärde, what is that? It's sort of the average outcome. Okay. So the expected value of a random variable is the outcome of that random variable on the average. So we talk about the expected value or mean or average of a random variable, and for a continuous random variable is defined as this integral here. So this is a number that we get by integrating the PDF of the random variable x and multiplying the PDF with the integration variable and do this. The expected value for a function of a random variable. First of all, what is a function of a random variable is a random variable. Okay, so if x is random, then if I apply a function to this, I still get something which is random. So it's another random variable. Luckily for us, the expected value for this new random variable is easily computed from the PDF of the original random variable. The only thing that differs between the two things here is what's multiplying the PDF. Okay, same PDF but different multipliers. Second moment of something is the expected value of the square of the random variable. And again, this is a particular function g, namely the square. G is the square of gx. So we'd simply, instead of g of u here, we write u squared. So that's the second moment. And then the variance is the expected value of x, the random variable, subtracted off its mean squared. Okay, so variance is the deviation from the mean, in a way. So the expected deviation from the mean, but squared. Okay, and we can find that simply through this function here. And expectation is a linear operator, and that's by definition here. It's linear in the input u. So the expected value of some scalar times x plus b is a times the expected value of x plus b. So it's nice for calculations. Questions so far? Also familiar? Okay. Then statistical independence. By the way, so this was all for continuous random variables. So if you want to do this for discrete random variables, just replace all the integrals with the corresponding summations, and all the properties hold. Independence, if we have two random variables x and y, we say that they are statistically independent if the joint CDF follows this property here. So the joint PDF of x and y evaluated at u and v, what is that? Well, by definition, it's the probability of the joint event that x is less than u and y is less than v. Okay, so we have two random things, and we would like to characterize the joint probability that these two random variables take on certain values. So if this is by definition. Now, if two things are statistically independent, that is when this equality holds. Okay, and the equality is that the probability of the joint event is the product of the individual events. It's the product of the probability of the individual events. Sorry. Okay, and these are just the product of the two CDFs. So in words, two statistical independent events are two uncertain things, but we have no reason to think they are related. So for instance, if I flip a coin in this room, that's a random event. The weather in Stockholm is also a random event. These things are unlikely to be related, so we model them as statistically independent. Okay. While there are other things where are clearly dependent on each other. Okay, so if we have this property here, then not only the CDF's factors, but also the corresponding PDFs. And if we want to date the expected value product of two random variables x and y, if they are independent, it's the product of the expectations. So it's quite useful. So any questions so far? Still familiar? Okay. All right, so let's talk then about what could potentially be random in our setting when we want to communicate information over a channel. And the first thing that we actually model as random, which is perhaps not super obvious, but we model the data that we transmit as random. So that the noise is random is sort of clear to us, but why do we model the data as random? Well, the data is not random for the transmitter. The transmitter knows the data it transmits. But from a receiver perspective, the data which is coming is unpredictable, right? Because that's the action of communication. If the receiver already knew the data that the transmitter would send, then there will be no communication problem, right? So the action of communication is actually for the receiver to try to guess what the transmitter sends. Okay, so the receiver is uncertain about what the transmitter sends, and therefore, from the receiver perspective, data is random. Okay. So let's talk a little bit about the transmitted bits. Okay. And now the discussion is from the perspective of the receiver, not the transmitter. So we model the transmitted bit. Okay, so the ith transmitted bit, which we denote by b subscript I. So I is a time index as a random variable, as a discrete, and then RV for random variable, not recreational vehicle. In this, it's random variable with probability mass function PMF. Then F for PDF or PMF, depending if it's a discrete or continuous random variable. B subscript BI, because that's the random variable we're looking at. And since this is a discrete, we do square brackets here. Okay, so what is this thing? Well, it is the probability that bi is equal to this number u. And since the bit could be 0, 1, we only need to specify the probability for one of these things. So say that this is equal to pi, the probability that the ith bit is equal. Okay, so it's pi when u is equal to 1. Okay. So with probability pi, it is 1. So what is the probability that it's equal to 0? Exactly. So it's 1 minus pi, right? It's either this, I mean, these two things needs to sum up to 1, because it's either this or that. There is no other possibility. So it's enough to specify one number here in order to specify this function, and therefore fully characterize the randomness in B. Okay. Very often, we assume that the bits are independent of each other, so there is no time dependency, which means that the probability for the ith bit is equal to the probability for any bit, so then we can drop the time index in this notation. So if they're equally likely, or sorry, if they're independent, then there's the same distribution for all the bits, and then we also assume that they're equally likely in the sense that it's equally likely that we have a 1 as a 0, so the probability pi is 1/2. Okay. So we normally assume that bits are independent and equally likely. Okay, so you will see this statement on exams and in books and so forth. So it's good to know what independent and equally likely means. It means that the probability that bi is equal to u is 1/2. Okay. For u equals 0 or 1 and all I. Okay. So this is the equally likely thing. Okay. And also, since there is no time, it doesn't matter which time index we look at. It means that all the bits are the same, so they're identically distributed. And the independence comes into the following thing. So if we think of B, what is the probability that B0 is equal to U0, B1 is equal to U1, etc., up to Bn minus 1 equals Un minus 1. Okay? So what is the probability for this joint event? Well, if it's independence, then we can write this as a product of the individual probabilities. So it's a product from I equals 0 to n minus 1 of bi equals ui, like this. So that's independence. And all of these factors is equal to 1/2 due to equally likely. So the product is simply 1/2 raised to the number of terms, which is n. So it's 1/2 up raised to the power n. Or if you like, is 1/2 over 2 to the n, which makes sense because 2 to the power of n is the number of possible bit patterns, so possible combinations of u0 up to un-1. So this is the number of different n-bit patterns. Okay. So in another way to say this is that all n-bit patterns are equally likely, right? And therefore, the probability of a particular bit sequence is 1 over the number of possible bit patterns. So 1 over 2 to the power of n. Okay, so in PAM, in the PAM block diagram, oops, sorry, we'll go forward here a little bit. There is this mapper that takes bits and spits out symbols. Okay, so let's look a little bit about that. We have something whose input is these bits, a sequence of bits, and then mapper, and outputs a sequence of symbols, amplitudes. These amplitudes is a member of one of these amplitudes. So AK is either A1, A2, or up to capital AM. So these are the possible outcomes of AK. Now, since BI is random, the bits are random, it's pretty clear that also the symbols are random. Right? So, since the bits are random, the symbols will be random. If these are equally likely, and independent, then the symbols here will be the same. So equally likely and independent. So a short example to illustrate this. Say that we have 2 input bits which produces 1 output symbol. Then the possible input patterns is 0, 0, 0, 1, 1, 0, 1, 1. And the possible outputs is capital A1, capital A2, A3, and A4. So these are the possible inputs, these are the possible outputs. We don't know which input will occur. It's a random event. So there is a probability 1/4 of each of these, and therefore there is a probability 1/4 of each of these. So to be a little bit clear, so let's look at this thing. So the probability that B0 is equal to 0 and B1 is equal to 1, that's this pattern here, is equal to the probability that A0 is equal to A1, right? Because they're coupled. Like if the input is 0, 1, then the output is A2, right? And the probability for the first event here is 1/2 times 1/2, because these bits are independent and equally likely. So this is equal to then 1/4. In general, in the M-ary case, the probability that any of these symbols, K, remember that K is a time index here, so the probability that AK is equal to some value, say A1, is equal to all the other probabilities, namely that AK is equal to A2, A3 is forth up to AM, and the probability for all of these is 1/m. Capital M possibilities, all of them having the same probability, namely 1/m. Okay. In this case, 4, so the probability is 1/4, and that's for all the symbols. Okay so far? Right? Okay. So now what we would like to do here, if we look in the block diagram here, if we assume that the bits are independent equally likely, we know that the symbols are independent equally likely, and then it goes through this pulse amplitude modulator. And we would like to say something about the signal here in terms of its transmit power. And to do that, we first figure out what is the energy required to transmit one symbol. Okay, and go from there. So Tx for transmitted. So the transmit pulse A times h of t. Okay, so if we look at this, so A is the data and h is the pulse shift that we use. Okay, so this has energy integral from minus infinity to infinity, A times ht magnitude squared and integrated for all times. Okay, so that's the energy of the pulse. We can write this as the magnitude of A squared times the integral from minus infinity to infinity, magnitude of h squared dt, like this. And the value of this integral is just what we used to call E subscript h. So this is the energy for the pulse. Now, the problem here, or the problem is just the fact that what we have in front of the integral here is A, the amplitude, the data that we transmit, squared. So since the data is random, the square of the data is also random. So this is a random thing. So the energy for this pulse is a random variable. So if we want to say something about the average energy, we need to take the expected value of this. So the average and I put average inside parentheses because we will not continue to say the average energy, we would just say the energy. So the average symbol energy what is that? First of all, there is a notation, so E and now S here as a subscript. So this is energy per symbol. E subscript H is the energy for the pulse. Okay, so just to make clear what this means. So the energy per symbol is, and then there is another E which is the expected value operator. So it has nothing to do with energy at all. So it's a little bit confusing, maybe the terminology here, but it's the expected value of this energy, which is the expected value of A magnitude squared times EH. this. So if we look at this expected value here, so we put EH in the beginning here, and then it's the that should be multiplying the expected value of the magnitude square of A. Okay, so how are we going to tackle this? Well, what do we know about the random variable A? Well, if we assume they're equally likely and independent and so forth, we know that the probability for A taking on a particular value is the same for all values. So assuming that we have equally likely independent bits, we have equally likely independent amplitudes. So this becomes pretty simple then. So, but to do this carefully, we need to sum over all possible outcomes of this random variable. And we know that there are m of those. So it's a sum from L equals 1 to capital M of the value of the outcome, which is AL, capital AL squared. Okay, so that's the outcome when small a is equal to capital AL times the probability of this to happen. Namely, the probability that small a is equal to large capital AL. Now, this happens to be 1 over m for all capital AL, so it doesn't depend on L. So we can pull that out to the of the sum if we like, and the result we have is EH times 1 over m times the sum from L equals 1 to m of capital AL squared. Okay. So essentially, if I know the symbols, I know the values, capital A1 to capital AM, then I can easily calculate this. It's only a function of the symbol alphabet and nothing else. And this is known as E and now subscript A for the symbol alphabet energy or constellation energy. So so this is the alphabet energy, or it's also known as constellation energy. So any questions on that so far? Okay. So to summarize what we have done so far is that we have said that the transmitted bits are random. And then we have made the assumption that the probability, the transmitted bits are independent and equally likely, meaning that all bit patterns are equally likely, equally probable to have been transmitted, which means that the symbols are also equally likely. We have now calculated what the average probability, what the average energy is for a transmitted pulse. And it's in terms of two things. The average symbol energy depends on the pulse energy and the constellation energy. It's two things that together determine the symbol energy. So a short example on how to calculate the constellation energy. Let's assume that this curly A is the possible amplitudes is -3, -1, 1, and 3. And if we draw that in a constellation diagram like this, we draw these points to indicate where the symbols could end up. So it's either -3, -1, 3, 1 or 3. And then the constellation energy for this is we take the amplitude, we square them, add together, and divide with the number of amplitudes. So it's 1/4, because there are 4 of these, and then -3 squared plus -1 squared plus 1 squared plus 3 squared. And if we add these things together, we get 20. 20 divided by 4 is equal to 5. Okay. So the constellation energy of this is 5. Okay? Right? So something to notice is that amplitudes which are far away from the origin contributes with a large portion of the average symbol energy, right? The energy goes up as the square of the distance from the origin. So this one has energy 9, and this one has energy 1, right? So it's, from an energy perspective, it's costly to move out from the origin. And that means that we would like to have constellations which are centered around 0, because I could take the same constellation and place it up here, and the constellation energy would be much higher, but the distance between the points, which is the important thing from an error probability point of view, will remain the same. Okay? So all constellations that we use are somehow centered around the origin for this reason. Okay, now for constellations that we use very heavily in practice are these Emery equidistance PAMs. Okay, so for equidistant Emery PAM, we have a constellation that looks something like this. We start in the origin, and then we put points to the left and to the right with the same distance between them. So we start by putting the first point here at some value, let's call it C. And then we take the other point and put it, the next point, and put it on the left-hand side at -C. We would like to keep the same distance between the points. Okay, so the distance is 2 times C in this case. So the next point we put to the right here is, okay, it's not going to be drawn to scale here, but it's at 3C. And we put the corresponding point on the other side at -3C. And we continue to do this until we have m points in total. And one can easily see that the last point here to the right would be m-1 times C. And to the left, it would be corresponding negative m-1 times C. Like this. So there are m/2 points here. On the right-hand side, and the same on the same side. All of them have the same distance between them. So equidistance means that they're spaced with the same distance. So what is the energy for this constellation? Well, it's if we just calculate the energy for the constellation on the right-hand side, and that will be the same as the energy to the left-hand side here. So we can just simply calculate the energy here and multiply that with 2. We have the total constellation energy. So it's 2 times 1 over the number of points we have to the right here, which is m/2, times a sum from L equals 1 up to m/2. These are the number of points we have to the right. Okay, and the Lth constellation point on the right-hand side here would be 2L minus 1 times C. Okay. Put in L equals 1, we get C, so that's that point. Put in L equals 2, we have 2 times 2, that's 4 minus 1, that's 3. So that's 3C, 5C, 7C, and so forth, right? So this is the points on the right-hand side of the constellation here. And we need to square these to get the symbol energy. The constellation energy. And now there is just algebra left here. And at the end of the day, we will get m squared minus 1 divided by 3 times c squared. Okay, and this will prove to be useful shortly. Okay, so let's take 15 minutes and continue after the break.